we'll start talking about experimental design. Okay? So we're talking about contractile state. We talked about cold shortening. We talked about how it's the combination of temperature and ATP. So if we chill a carcass or a muscle too fast, early post-mortem, while that muscle is still in fairly early onset, and it can even be a little bit later in onset, but when we still have a lot of ATP available, what happens is that with cold shortening, the sarcoplasmic reticulum does not have the ability to hold as much calcium because it's a membrane and it leaks calcium, and we have calcium flood with ATP. So make sure that you understand what causes cold shortening because it's very important. With thaw rigor, what happens, we have even more calcium release because the muscle is frozen prior to having ATP dissipated. So when it's thawed out, then we still have ATP available, but because during freezing we have ice crystal formation, the only way not to have ice crystal formation is to freeze it at -80 in liquid nitrogen. Right, and to freeze it very rapidly. Well, that doesn't really happen. And so we get some ice crystal formation, and those ice crystals will tear the tissue, we'll get tissue disruption, and of course the sarcoplasmic reticulum is a tissue. It is very sensitive. It isn't that strong of a barrier, and so we'll get a flooding of calcium, even more so than in cold shortening. And so we'll get more than rigorous contractions in thaw rigor than what we get in cold shortening. And I drew on the board, I talked about the differences in sarcomere length. 2.5 for a resting muscle. During rigor, we normally get down to 2.0. Cold shortening, 1.8. Thaw rigor, 1.5. So it shows you that there's actually the distance between the Z lines gets smaller and how much difference there is. Heat shortening is when we hold animals that are meat at a high temperature, above 16 degrees C, early post-harvest, and we have that rapid depletion of ATP, which results in rapid onset of rigor, but we also have, because it's at high temperatures, we're going to have a lot of calcium, and with that rapid ATP depletion, we're going to have some heat shortening. Heat shortening is going to be similar to cold shortening, to be about 1.8. So we get rigorous contractions, but not as rigorous as in thaw. And this is just a graph to show cold shortening and the relationship between pH and muscle temperature. So when we have pH greater than 6 and that muscle temperature is less than 15, that's the time that, the physiological conditions that we find result in cold shortening. And so, you know, if we're up here at 6.4, 6.5, and we get to cold temperatures, boy, we really have a problem. We're also, this shows protein denaturation, where we're going to have with higher temperatures and in combination with pH, we're going to get protein denaturation that we will not get that functionality back, which we get more with PSC. But I wanted to show you that graph. I skipped over it in the last lecture. So, fourth piece of the palatability puzzle is marbling. And with marbling, we know that we have a beef quality grade system. It's based on marbling and animal age. Animal age is in there for connective tissue, right? And the purpose of the quality grading system is the segmentation of a large heterogeneous population, called all the beef carcasses in the United States, and segmenting them into categories or smaller categories based on expected palatability or eating quality. So the idea here is that choice will eat better than select, and select will eat better than standard. We define eating quality as juiciness, tenderness, and flavor. Right? So consumers define it that way. When you don't ask them even about it, you ask about flavor, they'll still tell you juiciness, tenderness, and flavor. I didn't really believe that until I sat there in one-to-one interviews, and that's what they kept telling me, and I'm like, well, it works. It still works today. So marbling has been incorporated into the beef grading system since 1926 officially. And we have marbling standards. And if you're not familiar with those, I know Dorothy, you're probably the only one who hasn't seen these. So we need to show them to you. But it's the amount of intramuscular fat. And so you see this is slight. This is about 3% chemical lipid. And this is select. And then the small, modest, and moderate, those are choice. And these are going to be 4, 5, and 6% chemical lipid. And it doesn't have anything to do with the outside fat, only the fat inside. And when you can pull your slides up and you can actually see differences. And I'll show you my marbling cards, or we can pull some marbling cards to show you, Dorothy, so that you see what those are. And that amount of lipid, and that's what, this is the window of acceptability. And so I gave you chemical lipid because that relates to this green line here. We know that as the percent chemical lipid inside the muscle or intramuscular fat, as it increases overall palatability, and on these particular data, that was rated on a 1 to 8 point scale, with 1 being extremely tough, extremely dry, and extremely bland, and 8 being extremely juicy, tender, and flavorful. So you can see this starts at a 4, which would be slightly tough, slightly juicy, and slightly tender, and goes up to almost a 7. And you can see as chemical lipid increases, the green line goes up almost, it goes up very linearly. And that's an average of lots of data. Okay, so there's no error bars there, because in general, we could cite lots of papers. This is from Designing Foods, and it has lots of citations in there. I used to, again, give that paper too. It's a very good paper. I have it as a PDF if you'd like to have it. So, palatability increases as we increase fat. Well, what about overall palatability from a strip loin steak as measured using consumers or trained panel? What we see is that as we increase in chemical fat just a little bit, so I'm hoping I have this in a mode where I can draw on it. I tried. Okay, so when we go from 2 to 3, there it is, and I even oriented it. 2 to 3%, which is, well, slight is 3%, sorry. So this is standard. This would be traces, 1 to 2% chemical lipid. Notice that this palatability line is pretty steep. And so we see that most of the improvement in palatability occurs at very low marbling. And I don't even have that picture on here, but it's almost all red. You hardly even see any fat at all. So going from standard right here, I'll use a different color now that I can draw, from standard, which is going to be 1 to 2% chemical lipid, to select, we see that we make big improvements in palatability. When we get to 4%, I'm going to 4% right there. Sorry, I can't draw very good on here. All of this is choice, and this is select. So the window says that we, from a palatability standpoint, we need to be at least 3 to 7% chemical lipid to have acceptable palatability. And if we marry that with what consumers say they want from a diet health standpoint, it fits within a diet health standpoint as well. When we get above choice, up into above 7%, which is going to be this marbling score right here, palatability continues to go up, but not at not as high of a rate. And from a diet health standpoint, people don't really like to eat prime or that high a percent chemical lipid in their meat on a consistent basis. The other issue is that this meat's very expensive. We only produce about 2% of the meat produced in the U.S. is prime, so it's very, very expensive, and it's usually only served at white tablecloth restaurants. But notice here, I'll try to use a different color. So when we go from 1 and 2% chemical lipid to 3, we saw that there is a pretty steep curve. When we're in choice, notice that the slope of that line's not as great. So we still see improvement, we just don't see the big changes. And when we go even above 7, the slope of that line's even a little bit flatter. So increasing marbling above 7%, once we get to 7%, doesn't really give us any improvement in palatability. It'd be hard to measure. So this tells us that we want to eliminate standards less than 3% chemical lipid, and that we really have, and when we get to these higher marbling, this is going to be a specialty market, that most of the meat that we produce needs to be in the selected choice range, right in here, the window of acceptability. So that sounds great, doesn't it? It looks good, nice lines, slopes are there, we increase marbling, we increase palatability. But the slopes aren't linear, are they? This is a steeper slope, then it levels off, then it levels off more, meaning that it's not linear. And there are people who have removed marbling from their grading standards. There are countries that have not ever had marbling in their grading standards because they don't really believe this relationship. When you either run a correlation or a regression equation, you really marbling only accounts for 10 to 20% of the variability in eating quality. It's not very high. That means that there's 80 to 90% unexplained variation. On average, though, we see that it improves. How does marbling work? There are 4 theories. One is the lubrication effect. In the lubrication effect, it says that when we look at meat when it's chilled, we can see the marbling. It's hard, but when we cook it, it gets liquid because it's an oil. It's a fat base. It's triacylglycerides inside an adipose cell. And so when at hot temperatures, that and here's, we'll just say that this is a muscle fiber. It's a long cylinder, isn't it? And here's another cylinder. And if we have more fat, we're going to have liquid oil in between. So that when we bite down on this, they're going to slip. So they lubricates between the fibers. If we have low marbling, and we don't have very much oil, we're going to have less slippage. It's going to require more force to bite down. So this is low, and this is higher, okay? And that's the lubrication effect. It's like a piston in an engine. If you don't have oil, it doesn't move. So standard is no oil in the engine, prime is lots of oil, right? The second theory is called the bulk density effect, and I call this the Swiss cheese effect. So this is lubrication, and now we're going to talk about Swiss cheese. Lipid is softer than lean. And so if you look at a piece of Swiss cheese early on in its manufacture, it's solid. And so this is early. But as it ages, CO2 is produced and you see holes. And those holes are like marbling. And if you were going to apply a standard level of force on both of these, it would take more force to segment this solid piece than the piece with the holes. So if we have more marbling, and marbling is soft, so that's soft, and the lean portion here is harder, it makes sense that if you have more marbling, it's going to require less force. And notice that it isn't just one of these things, it's a combination of all of them. The third theory is the insurance theory. And for insurance, as we cook meat, heat transfers in the meat. So if I have a steak and I put it on high heat, like a grill, the heat's going to go up into the meat. Heat denatures protein. So if this change is more, or let's just say the more heat for longer time results in more protein heat denaturation. When proteins denature with heat, remember proteins, we're mainly worried about the long proteins that have side chains that hold water. So in normal, they're going to go through rigor, and yes, there's going to be slight changes. Their side chains, like my hands here, are going to lose some ability to bind water. But if they have heat denaturation, because they've been exposed to heat more to a greater extent, then they're going to fold or unfold. They're going to lose their ability to hold water. So we know that fat is an insulator. So if we have higher fat, heat transfer is slower, and we have less heat denaturation. So the proteins don't denature. When they denature, they lose water, they become tougher. So higher denaturation equals tougher. So if we have more marbling, it's going to be a protective effect against protein heat denaturation during cooking. To totally prove this, we're going to Utah sometime to do some measurements on part of Michael's thesis project. Because it's been hard to prove this, but when we have choice and select samples, the choice samples, whether we're measuring shear force values, consumer evaluation, or training panel evaluation, choice overall is better than select. And we tend to have a little bit higher cook yield. Maybe not always statistically, it might be hard to measure, but a lot of times we see that with choice versus select. And instead of showing you lots of data, I'm going to ask you to keep, or to take my word for it, okay? And then the last theory is the strain theory. Strain theory. And in the strain theory, we know that we have muscle fibers. Remember this? Myofibrils, right? Myofibrils, and then inside of our muscle fibers. So I just put, here's our muscle fibers. And muscle fibers have paramecium around them, don't they? This is paramecium. Marbling actually evolves in the paramecium. Adipose cells, when we see adipose cells, they develop in paramecium. So when you see the marbling out there, that's fat in the paramecium between muscle bundles. That's pretty neat. Well, paramecium is like a big elastic cover, isn't it? And so adipose cells, as they develop, it's like poking a hole in this elastic cover. So it weakens. The result is then, by developing marbling, we weaken paramecium's contribution to tenderness. So marbling doesn't just do one of these things, it contributes slightly in all these factors. And the Canadians pulled marbling out of their grading system in the 80s when there was such a big emphasis on lean production. They said there's 10%, 20% of variation. We don't need it. Too costly to measure something that only accounts for 10 to 20% of the variation in tenderness. And they only had a system based on lean assessment. In the 90s, they put marbling back into their grading system because they also noticed that with time, as they measured their meat in Canada, it was decreasing in palatability. And they were trying to compete with the US for the Japanese market and some higher palatability markets, and they were losing. And so they had to kind of say, all right, their meat scientists kind of had to lose face a little bit, admit that they were wrong, and they put marbling back in their grading standards. When I was in Brazil, that's what they were arguing about at the meeting, was should marbling be in the grading standards? Because they have a whole group of scientists that say when we measure marbling and then we measure tenderness, whether that's mechanically or with humans, either trained humans or consumers, they can't tell a difference. And if you only measure a few samples with a low N, that may happen. But when you look at it overall, and you have enough N to really test that hypothesis, we find that it accounts for some variation. Right? So, marbling. Yes, Mark.
Is there a possibility that the reason that curve past choice and on up to prime flattens out so much is because the vast majority, I mean, other than certain breeds, like the Akaushi and the Wagyu and all that a lot of the cattle that end up grading prime are older. Maybe not older as in
not older,
maturity.
but a couple months, because
Right,
they've been on feed longer. It could contribute to it, but as you know, there are animals that can feed them forever and they'll never marble.
Right.
Those that will marble earlier. And that probably is accounting for the variation and why it doesn't account for a lot of variation, because it's always interesting to see why they marble, why they don't. But, you know, it could contribute a little bit. It probably helps some of them. It does, because if they're a little bit older, they have a tendency to be up there putting less energy into growth, and they're putting more energy into fattening and the fattening phase. And depending on there are lots of things that contribute to that, what kind of fiber types they are.
Yeah, I should know maybe like there's an increase. I mean, yeah, you're increasing in fat when you get to that last end of the finishing stage. You're increasing marbling, but it's also probably still increasing in the amount of connective tissue. And
it is, and as long as you're on feed in a high concentrate diet, you're probably okay from a connective tissue contribution. Good question.
so it's more like the reason for the increase in price is more of a niche and the limited availability.
Right, it's supply and demand.
Yeah.
Probably drives it.
Yeah.
Okay, so last factor, animal age and beef tenderness. We know that we have A, B, C, D, and E maturity classes. Saw that in the previous slide. That's the other part of the quality grading system. And as animals get older, and these are the classifications, we know that their collagen solubility decreases, right? And they're going to have darker color, and they're going to have stronger flavor. I don't know about this is one of Liz's, I don't know about waterborne capacity, I didn't have that. So that's going to be important. This is an important slide, and I'm going to, this goes back to marbling. Within young cattle, and we look at marbling's relationship. This is the 1005 carcass study. And actually, as a graduate student or as a meat judging team member, before I went to graduate school, I helped collect some of these data. So the data is a little bit old, but it still holds up because all the consumer work that we're doing, it still holds up almost exactly like this does. So this is published in 1987 the Smith et al. I just have to erase it. So what this is that USDA funded this project, multiple universities were involved, they went across the United States and they selected standard, select, choice, and prime carcasses. They removed the ribeyes actually from those carcasses. And they did trained sensory panel. And they used the 1 to 8 point scale that we use. A 1 is extremely tough and dry and extremely intense in flavor. And an 8, it's the same scale as in the window of acceptability, is extremely juicy, tender, and flavorful. Okay, so 1 is bland. I think I said that wrong. So anyway, what did they find? And this is just averaging across those 3. I will tell you, tenderness probably played a bigger role in this than juiciness and flavor. So use that with a grain of salt. But these boxes represent the scores that they had for the meat that graded from the standard carcasses. So you see that they had some standard carcasses that rated a 6. And I put this line here at a 5. And because I said, well, that's really minimally acceptable. And a 5 would be slightly tender, slightly juicy, and slightly flavorful. So, I mean, I think our line's probably 6 today, right? But that would be the minimum that I'd find acceptable. I think most people find acceptable. So we have some standard carcasses that ate above a 5. On average, our standard carcasses are eating about 4.3. Notice that, though, we have almost 60% less than 5. So we have, if we're rolling the dice and the standards, we have a 60% chance of having an unacceptable eating experience. And remember, standard is going to be here at 1 to 2% chemical lipid, right? When we go up to 3% chemical lipid, to select, the biggest change is we see a reduction in the size of the box. So we see less variation. And we see only 25% less than 5. On average now, we're at about 5.3. I can't get this to draw it where I want it really exactly. So we get a 1-point improvement in palatability by going from standard to select. And that's what that line on window of acceptability was trying to show you as well. When we go from select to choice, and remember that choice is going to be the 4 to 7% chemical lipid. And again, the box moves over, but we're really up here at about 5.8 on average. So on average, we see a 0.5 point improvement. So we see, remember that change in the slope? It really, we see a big difference. I always, when I talk to producers, I ask them if they played Mother May I. And you know, this is a giant step, and this is just an average step or improvement. And so this is a big improvement. We see a 0.5 point difference improvement overall, and we only have 10% less than a 5. So we see that there's a change. When we get to prime, again, we see an improvement, and this is at about 6. I can't draw straight, and it doesn't draw where I want it to be anyway. And we only have 5% less. So marbling still has a relationship, and if we connected the dots between the means, we'd have kind of a linear relationship, wouldn't we? But there's a lot of variation about that mean, right? And sometimes you have a standard right here that eats better than the choice up here, doesn't it? So you have to have enough numbers, sufficient numbers, to be able to see a difference. And when I was in industry, because the company I worked for had a feedlot, a packing plant, and a further process plant, when I would we'd bring customers in that were trying to sell them on our choice program, because it's worth more, we want to move more choice. We'd take them to the feedlot, explain how we fed our cattle, then take them to the packing plant, show them how we harvest and fabricate the carcasses, and then take them to our portion plant and cook some steaks. If the choice ate better than select, I was the cook and the driver and the tour guide. If they had a choice that was here and a select that was here, I was, oh, by the way, this is Dr. Rhonda Miller, Director of Research. Ron, why don't you tell us why the Select ate better? Because if this was perfect and we had 100% of the variation was associated with marbling, there would be no overlap of the boxes. But because of variation, the boxes overlap. And that's, the Canadians said, well, if there's overlap of the boxes, throw it out. The Brazilians said, oh, and originally that's what they were arguing about. They're like, too much overlap of the boxes. That's basically what they were saying. That's not how they said it. And then the person arguing against it would go, yeah, but there's a linear improvement. And consumers can tell a half a point difference on this scale consistently. So marbling has a relationship. And I've talked about the marbling theories, and now I have to erase all this to get it off of there. Isn't that cute? And this is just a review of what we've already talked about. It has pictures on it, though. Oil, the lubrication effect, oil in the engine, the bulk density effect. See, that's the Swiss cheese with the holes, fat and lean. Insurance theory is, notice here we have choice and select, and these are top loin steaks, and these are shear force. So a higher value means they're tougher. And we cooked to 4 different internal temperatures. There's a lot of N for each dot here. This is the big choice select study we did in the early 90s. And notice that these samples sheared the same at lower degrees of doneness, but when you get to higher degrees of doneness, the select are tougher than the choice. And that's that heat denaturation issue. And then the strain theory, see, here's the muscle fibers. My picture is not quite as good. And there's paramecium, and there's the adipose tissue in the paramecium, right? Oh, scuba diving. Also, we know that when we have higher marbling, we get meat that's perceived as being juicier. When you eat a piece of meat that has more marbling in it, you bite down and it releases the fat, your salivary glands go, ooh, fat! Because part of the job of the saliva in your mouth is to start breaking things down before they get to your stomach. And fat's hard to break down. So we just have an innate, whether we think about it or not, response to fat in our mouth. And it usually is increased salivation. So we perceive it as being juicier, whether it is. And fat usually squirts too. So if it's higher fat, it squirts out with the juices. And we perceive it as being juicier. And we also perceive it as having fat flavor. Tanner's project, thesis project, and then before him, Rachel Glasscock's, which is the most recent research we've done with consumers and flavor, where we really look at flavor. The one sensory attribute that always and consistently goes with overall like for consumers is fat-like. And we give them select and choice, and we give them some different cooking methods, and we do lots of things. And you know what? They like it, the fat. They like the fat. So we know that increased marbling is also related to juiciness and flavor. And when we talk to consumers, remember what I said? They don't, if we try to talk about tenderness, they tell us about juiciness and flavor. If we try to talk about flavor, they tell us about juiciness, flavor, and tenderness. All 3 of those are in their mind as far as eating. And they usually talk about them. They don't separate them like I do. Or you might, because I trained you to think about that way, okay? So, we know that total amount of fat is related to flavor, but also the fatty acids that are part of the fat. Fat in meat is 99% triacylglycerides. So that's a glycerol backbone with 3 fatty acids attached. We're going to talk about that in a little bit more detail later in the semester. And those fatty acids are susceptible to oxidation. And during heating, they oxidize. They have heat denaturation and oxidation. And they produce carbonyl compounds. We should ask Tanner what they are, because he's measured a bunch of those. And that's what Hannah and Michael are going to be measuring when we're gone, so just to let you know. And they affect flavor. And we like some of those. We found out that actually the flavor compounds, they like fat. They want fat in their meat, and then they like pyrazine, which are compounds that are associated with using high heat, like a grill, for a longer period of time. We also know that those fatty acids can go through lipid oxidation or affect flavor. So that release of the flavors associated with fat, consumers like. And they do affect the overall flavor. And we're going to talk more about that. So connective tissue, it's the total amount of connective tissue and the percent solubility. Those A, B, C, D, and E maturity are there because older animals have more connective tissue, but mainly because the connective tissue that's there is less soluble. Right? We've talked a lot about that. And so amount and solubility. These are some cow steaks. The lighting's pretty good here. What do you think of those steaks? They have a lot of marbling, don't they? These are some steaks I served to some chefs in the Caribbean and Mexico, in New York City. Look pretty good, don't they? They're kind of dark in color, aren't they? They should be brighter cherry red. They look beautiful. They were tough as nails. They also tasted more livery and serumy. And we really picked that up. So we can get them to marble. We can feed them older animals, and we can get steaks that look good and have marbling, but that doesn't take away all that connective tissue. All right? So these are the 4 pieces of the palatability puzzle that we talked about. And we spent a lot of time on aging effects. And we spent a lot of time on all of these because now we're going to go into the part after we talk about experimental design where we're going to talk about how we can influence each of these 4 pieces with pre-harvest and post-harvest factors, right? How we manage these things, how we manage these basic principles. Any questions? And I did get through all the papers, right? Oh, the Sullivan-Calkins paper, that is the one I didn't want to mention. That paper, I gave that to you really more for a reference paper because in it, in Table 1, this is some of the base information used in the bovine myology website that talks about differences in tenderness across different muscles. And so this paper, I wanted to give you this because it just classifies muscles by tenderness, and then it has this Table 2 in it, which is wonderful because it has a list of lots of articles that are background articles for you to use. And Table 2 is just incredible. It goes back to the Ramsbottom papers in 1948. So this paper is a great how do cuts differ in tenderness, and it should convince you that cuts do differ in tenderness, and they talk about some of the factors associated with it. Of course, most of that between cuts is connective tissue. So that's what, I'm not going to ask questions about that paper. It's really more there as a reference paper. Any questions? I'm going to change a little bit here, and I might have to have, I didn't pull it up. Let me see if I can pull it up. Okay. Oh, I can. Oh, it's so fun to be able to touch it and something happens. So now we're going to talk about experimental design. And I've never known really where to insert this into the class. I've inserted it at the end, I've inserted it at the beginning, and so I actually found out that inserting it between, at this point in the semester, after we've talked about some papers, usually makes it more effective. If I do it too soon and assign you your hypotheses and start getting to work on those, everybody procrastinates and you kind of lose the effect. Remember, part of your grade is to write a paper in here, right? 6 pages maximum, not huge. You have to have a minimum of 5 references, and if you have over 10, you've overdone it, right? And you usually tend to build more, get some initial references and build from there that are more materials and methods. So we're going to talk about that. Probably not. I'll probably end up spending the beginning of thirsty talking about the paper more specifically. But we started to read some papers, and I made a big deal about giving you the Nishimura papers with an N of 1 and an N of 3. And then I just talked about marbling and said you had to have sufficient N to test the hypothesis. And if you have an N of 10 for treatment, probably not enough. And I've reviewed research papers for the cattlemen and for the pork board for years, and also for USDA and other people. And one of the things that's the biggest weakness and why projects don't get funded is that their experimental design is not correct. And when you're reading papers, understanding their experimental design and how that strengthens and limits the interpretation of their results is really key. Because if you're going to do prelims and you stand up and you talk about Nishimura, then Nishimura presents some good thoughts, right? But I'm going to tell you, 1 or 3 black Japanese Wagyu steers, it's hard to take those results and interpret them to the United States beef population. First of all, because we don't have that many black Wagyu steers in our genetic pool. We don't feed our animals the same way that they do. We have a lot more variation genetically. We have a lot more variation from a marbling standpoint, from lots of factors, and our animals are younger. There's lots of differences. But I still gave you those papers because they really presented some interesting thoughts, didn't they? So understanding the experimental design and how you interpret it is really key to the next step of being a good scientist, and to examine. And one of the things that we feel as a faculty that's happened with our students is that we don't examine enough, that we don't think, that we don't challenge. And I can remember a student that was in this class in the past, who's a good friend of mine, and I used to present the Kamari 1988 article, and I did this on purpose because it kind of aggravated him. I'm like, Kamari is not right here. And I'm like, how can you say that? It's in print. So? Data doesn't support it. Read it. Look at it. Think about it. Because somebody says it doesn't make it true. Right? Yeah, I review papers all the time for journals, and that's what I'm looking at. I'm looking at whether they, the interpretation of their results and the data they presented, is that valid in relationship to what they measured? Did they measure the right things? The method that you measure something with affects interpretation. Tommy Wheeler, one of my dear friends, it's on video so I can show Tommy this. Him and I, well, Tommy and Steve and Andy, all the guys at Clay Center, I am not a huge proponent of slice shear force. They will only do slice shear force. And we've had many an argument about it. And it's okay to have an argument about it, or a discussion about it. But I find that the slice shear force is too variable. And it doesn't have as high a relationship. Yeah, Wheeler et al. 1999 showed a stronger relationship with the cattle that they used in that study. But I'm in 2014 with animals that are representative of cattle, I think, from the U.S. today. So, doesn't mean that they're wrong and I'm right. It means that there's a difference in the measurement tool. And that's okay. And sometimes we forget that. So what I'm trying to get you to do with the experimental design is try to increase your understanding of experimental design and how that impacts interpretation of data. I think that's one of the hardest things to do. When I was in graduate school, I think I was very fortunate. First of all, I was in a smaller department. It really isn't that much smaller than the animal science department, but we weren't segmented by sections. So when we had to work cattle, our cattle, we had people in animal breeding and beef cattle production and processed meats, and everybody had to come work cattle. And then when we did things together, we also had to go help them with their projects. We talked about things, and we didn't always agree. And when the Journal of Animal Science came out every month, our department head, who weighed 330 pounds, is 6'6", had the biggest booming voice, and we're all scared to death of him. If he saw us in the hall, he'd say, "What did you think about that Averly paper?" You better have an answer. "Oh, sure, well, and he was an animal breeder, so he was like, well, he was tremendous, had a tremendous gift as far as being like a photographic memory. So he'd already know experimental design, so you better know it. Because he'll say, well, do you think you had enough cattle? What do you think about calf versus yearling feeding? Do you think that applies to yearling feeding? So you better have some answers, because you didn't want to be taken on assistantship. You didn't want to tick them off. And so it forced us to read much more and to talk amongst ourselves. Because boy, if we were moving down the hall with 4 of us, he kind of expected all 4 of us to know an answer, regardless whether we're an animal breeder or a meat scientist or a production person, okay, or a nutritionist. Oh yeah. So that's what I'm going to try to help you to know, because see, we talked about those things, and I don't think we talk about them enough now. And I want to improve your knowledge level of questions to address using experimental design, and to improve your comfort level with practical statistical analysis. That's really the purpose of this, because as a faculty, we sat down and said, we aren't getting enough of this into our students, so they wanted me to add it to this class so that we could start that process. And that's also why I put the articles in and try to talk about the strengths and the weaknesses of the articles. We also talk about that even in RMC, we don't do enough of challenging each other, and that was at the RMC Planning Committee when I was gone to Lincoln a couple of weeks ago, because it used to be people stood up and challenged. So Dr. Zerl Carpenter, when he was faculty member here, I knew about him even though I was at Colorado State, and I knew who Dr. Bob Kaufman was at Wisconsin. And when you go to animal science meetings or RMC, if an A&M student stood up and presented data, Kaufman would ask them hard questions. And then Kaufman and Carpenter sometimes would get into this big discussion. And everybody thought they hated each other. And then Carpenter did the same thing to Kaufman's students. And that was always like, oh boy, it's going to happen now, And everybody thought that they hated each other. They were college roommates. They grew up, they knew, they've been best friends forever, right? So, but they created that environment because that's the environment they came from Wisconsin. And so that's, there's nothing wrong with that. One time we walked out of a meat science seminar and somebody said, well, I guess you and Dr. Smith are mad at each other. I'm like, are you kidding? We just had one of the best conversations we've ever had. Yes, yes. Yeah, we don't always agree. We think of things differently. And so, and at Clay Center, one of the things I learned, because they treated me like a scientist when I was there, was to question and have discussions. Because I would sit there and watch some of the people with the brightest minds at the time sit and talk about things. And I didn't always have anything to contribute, but I certainly learned a lot. So, what are some of the biggest things you need to know? And I know that you've been trained in the scientific method in many different ways. It's why we have you do a thesis project or a PhD project, and you're involved in multiple research. And I know that Dorothy has to be involved in lots of different projects over in her own lab. And we know that it always starts with the hypothesis. So you have to state the hypothesis. Now, I did find out last year that Keith Belk teaches, Dr. Keith Belk of Colorado State teaches a seminar class, and he tells our students he gives them an argument about not stating their hypothesis. I just was appalled. I helped train Keith. We've been friends since he was in high school. So I gave him a hard time. I'm like, what is this about a hypothesis? And he just turned red. because it's kind of, the students interpret it as that they're never supposed to say what the hypothesis is. How can you teach them to not state a hypothesis? Our scientific method is always based on a hypothesis. So you have to understand what the problem is. And you need to know what you're going to examine. And you need to define the objectives of your research. So you state your hypothesis because all of these things are starting to define how you're going to test your hypothesis. The one thing that you need to understand is because you have a hypothesis, there's lots of ways to test it. There isn't one design. And I'm going to give you, you're going to get to draw here at the end of class. I have 12 hypotheses. And Kelly, you don't have to do this, you know that. I didn't get one for you. And
That's okay, I've done this many times.
I know, you do this all the time. This is your job. So I don't have any expectations on how you're going to design a study to address your hypothesis. I give you. All right? You get to do it. And I've used these hypotheses for many years, and nobody has ever repeated a design. Now, it doesn't mean that somebody did a better job than another one. That's not what it means. One of the things I'm going to do with you is we walk through your paper and you write your paper and you design your study. Because I'm going to work with you one-on-one. Is that I want you to understand when you make a decision about what N you're going to use or what treatments you're going to use or how many harvest days or how many reps you're going to have for a day, how that interprets or how that influences the strength of your data and interpretation of your data, okay? And when you decide what population you're going to pick from, some of these are pretty broad, and so I give you a lot of options. You know, if you're doing a lamb study and you go out to, and you're at University of Wyoming and you go out and use the lambs that you have at your research station, you have to question how representative are they of the U.S. population. Since Wyoming has one of the largest sheep populations, they're probably pretty representative, right? But if you go to Mississippi State and do the same study, you probably don't have the same type of animals and the same genetics, and it may not be represented. But you may also have chosen that population because you don't have as much variation, and by applying a treatment, if you find differences, you're pretty sure that treatment's it is different. There are different ways to approach it. So you have to understand that first you state your hypothesis. That's why I'm giving you a hypothesis. And from that you start developing how you want, uh-oh, I did it twice. I'm sorry, Blythe, can you just use the arrow to go back?
One more?
Yeah, go back. Okay, there, thank you. So, how do you do that? And those that are in seminar on Friday, and I know you hear this from your major professors all the time, but the first thing you do is you go to the literature. I can't tell you how many, I love the library searching. I love, because that's so much easier than walking over the library like we used to have to do. It's so nice. And I get carried away and then I get like 100 papers on my desktop and I'm like, oh, well, why did I get all those? Oh, that means I have to read them. Oh, I don't read all of them. I read part of them, right? But you have to go to the literature. You have to know what's been done, and you have to know when they did it. You can't just read the abstract. You have to know how they designed their study, what the interpretation of their results, and you interpret what you think they found. You don't read just what they said, because they can be wrong. They're biased. When they're not supposed to be, but we all are biased, right? You know, Bos Indicus versus Bos Taurus cattle, I'm biased, right? Even if the data says one thing, I mean, I hope that my biases don't cloud my judgment in discussing something, but we're all human. So you look at the data they present, an experimental design that they define, so you have to put all that stuff in a paper, and you decide what they said. And then you can read what they said and see if you agree. That's actually kind of fun to do sometimes. And you need to not reinvent the wheel. A former student that was up here was great about reading things. Or, well, he'd read one paper and then he'd come in and say, well, I think we need to do work on this. I'm like, no, well, that's called Wheeler et al. 19 1998 or something, you know, Kringle et al. I'm like, go and read those papers and then come back and let's talk about it. Because you can't just read one paper, you have to read them all. And I know that it's difficult to do literature reviews. I love to do literature reviews. And when I was at Clay Center, I had articles stacked in the back of my office that were different topics, you know, because I'd find, oh, I gotta have that paper too, you know. And so it helps you to understand what's been done and where the science is so that you know how you can contribute to science. It's one of the biggest criticisms editors have. And if you ever want to listen to somebody, you should listen to one of the past RMCs. I can't remember which one it was, that Howard Swatland did a talk on this, and it was classic. And if you don't know who Howard Swatland is and you're a meat science student, you need to know who he is. Anyway, I'm not going to tell you. University of Guelph is where he spent the last of his last days. Anyway, very, very intelligent man. But what he said is, do you know how many of the papers I see as editor of Meat Science that do not contribute to the scientific literature? You know, we do some work that's confirmation of a past principle, right? But that gets old. How many confirmations do you need, right? And that's one of the biggest challenges that you have as a student and your major professors have in publishing results is how does that contribute? So that's what you have to do. You can't reinvent the wheel. And you don't do literature searches just at Texas A&M. And I reviewed an article that was from an institution that I love, not here, and they only cited their own work. I think I made a few comments that they could tell who it was that probably reviewed the paper. I'll just tell you, it's my major professor, other major professor, one of my major professors was an author. I was really disappointed. I'm like, you didn't even recognize anybody else, and there's tons of work in that area. You don't get to just cite your own work. And I realized probably the graduate student wrote it, and that's all they did. But you need to look at other people's work. Because whether you agree with them or you don't like them because they're from a different university, it doesn't really matter. Everybody's smart, everybody approaches things differently, and they contribute to your knowledge base. I can't emphasize that enough. What do you need to extract from your research articles and literature review? I used the example of sodium lactate. It's one of my first papers here. That was that's been one of my classic contributions to scientific literature, was use of sodium lactate in pre-cooked roast beef to extend shelf life and how it impacts palatability. I will just tell you, I already did the work when I was at Montfort, but now I'm not in, and I got to come here and they thought I was really smart. So that's okay. There's a lot of stuff in industry that they know that they can't publish. So sodium lactate, what's currently known? Well, sodium lactate has been used in the bread industry. It's been used in the soup industry. It's used in the medical industry. It's used at high levels to make people throw up after they consume poison, because at high levels it's very caustic. So you go out and find out all that kind of stuff. And then you develop a working hypothesis. And our hypothesis was, does addition of sodium lactate increase shelf life without impacting flavor or palatability in a negative way in pre-cooked roast beef? And you need to look at what other researchers have done and look at the advantages and disadvantages of their methods. You need to know how they measure things, how much variation is associated with it. You don't just look at means. You actually look at standard errors or standard deviations or residual mean square errors to understand what their parameters were. And that's hard to remember. I used to write it on little note cards. So if I saw Dr. Jones coming down, I'm like, ooh! Yeah, I know what those papers said. Yeah, I think he always thought it was really weird.